Okay. I'm going to talk about something that I've been interested in for a really long time, ever since I first learned a little tiny bit about Bayesian networks when I was a PhD student at Carnegie Mellon in the early 2000s. And the first article we had to read was called Bayesian Networks Without Tears. Um, but it's about blending the traditional ways of modeling the movement of contaminants in the environment, which rely on an understanding of fundamental physics, chemistry, and biology, with Bayesian networks. And I'll have to give a big caveat. The way I've done this so far might be totally wrong, so I'm hoping maybe some folks in this room might tell me there's a better way to do it. But just a little bit more background about me. I'm really a mathematician at heart. I got an undergrad degree in math, worked for a little bit, decided I wanted to become an engineer. So I went back to school and got a master's in environmental engineering, worked for 13 years, ending up finally at a think tank called the Rand Corporation, where I was opening an office in Pittsburgh and hiring a lot of PhDs from Carnegie Mellon. And I found out about this amazing program called Engineering and Public Policy. And one thing led to another, and a guy I hired said, you know, you could really go talk to them and go back to school. I didn't believe him, but it happened. And then while I was there, I thought I should also get a degree that people knew something about. So I got a dual PhD also with civil and environmental engineering. And I wanted to add to my degree training here, BayesiaLab introductory and advanced courses. There's Stephen and I, Seattle. We were trying to figure out what year it was. I think it was 2016, but maybe 2017, something like that. Yeah, we did the introductory one in Cambridge, both of us, and then we both showed up in Seattle for the advanced one, which wasn't too much after that. So, yeah.
About 30 pounds ago.
And a fewer gray hairs for me. um, so right now I'm head of the Department of Civil Construction and Environmental Engineering at North Carolina University. State University, sorry, which is the main engineering school in the state of North Carolina. But I've held some previous positions as well at other universities. Did Alex leave already? Because I spent some time at Indiana University. I went to talk. Oh, there you are. Yay. And I thought there was, yeah, we should follow up. But anyway, so that's a little bit about me. So I'm going to talk about a particular application problem of where I've tried to blend these traditional ways that I learned how to try to predict the movement of contaminants in the environment as an environmental engineer with Bayesian networks by looking at a particular case study problem. So I'll tell you about that. And there were two objectives to this study. One was to identify the cause of a very unusual pattern of contamination that the State Department of Environmental Quality had observed that really didn't match the predictions of the traditional models. And the other was to find areas that hadn't been sampled yet where they should maybe test and see if this contamination was present. So again, I'm using BayesiaLab with and without some input from mechanistic traditional models. And then I'll tell you what we found out about what was causing this unusual contamination pattern and which of the models were most accurate. So the problem in this case is there is a region in North Carolina where it really hit the news in around 2016 or so that this strange chemical had shown up in the water supplies. Some researchers were out just testing rivers in the state to see what kinds of organic contaminants are we seeing there. And there was this big signal from a chemical they didn't recognize. It turns out it was a proprietary chemical manufactured by Chemours, formerly DuPont, which is called, its trade name is Gen X, which is kind of funny if you think about the other meaning of Gen X. But it's the trade name for a contaminant called hexafluoropropylene oxide dimer acid. I'm not a chemist, but this chemical structure here has got 6 carbon atoms, those are the gray ones, and then the kind of light blue ones are fluorine atoms. And that bond is really, really strong, giving these kinds of chemicals special properties. So it's in a a family of chemicals called per and polyfluoroalkyl substances, which you might have heard about. These chemicals are synthetic organic chemicals that were developed in the 1930s, really by accident by a chemist at DuPont who was really trying to create a new refrigerant gas and kind of accidentally produced the first of these PFAS contaminants, which became Teflon. He discovered it had all of these properties. Um, anyway, discovered accidentally, but really widely used since the post-World War II period. Some of the uses, initially Teflon pans, nonstick pans, but the properties of these chemicals, that really strong carbon-fluorine bond gives them all these extra properties: stain resistance, water repellency, oil repellency. Some of them have surfactant properties, heat resistance. And so they have become really, really widely used. And it was only in the late 90s, early 2000s that people started to realize, wow, these contaminants are associated with a wide variety of systemic risks to health. They can accumulate in the human body. They've been called forever chemicals because with that really unusually strong carbon-fluorine bond, it's one of the strongest bonds known. They don't break down in the environment. So obviously they also aren't easily broken down in the human body. So these are some figures that you might see if you look into some research on health effects of PFAS. They have been associated with many different adverse health outcomes. And if you want to see a very compelling story about kind of this really hitting the news in the US for the first time, it was in the early 2000s in Parkersburg, West Virginia. A DuPont facility had contaminated surface water and drinking water supplies all around the town of Parkersburg. And it turns out they had known for a long time about the health risks, but it really covered it up. And this farmer's cows started dying. And so this is the story of uncovering why these cows were dying, and then the lawsuit that resulted against DuPont. And so anyway, there's this Hollywood movie. Has anybody ever seen Dark Waters? Oh yeah, it's a really good movie. Recommend it. But I'm going to talk about, so that case in Parkersburg, West Virginia, really kind of this discovery was in the late 90s, early 2000s. Fast forward another 15 plus years, and we have a similar episode in North Carolina. Now, in Parkersburg, West Virginia, the contaminant that was being manufactured, or the chemical, was called PFOA. It's one of those carbon-fluorine compounds. It had a chain of 8 carbons bonded to fluorines. Because that was discovered to be harmful and there was this big lawsuit, DuPont said, well, let's substitute it with something else. And they started making this substitute, Gen X, which has only 6 carbon atoms, so it's a shorter chain. And they were making a lot of it in North Carolina. And again, some colleagues, chemists, discovered this widespread in the water supplies, particularly in the southeastern part of the state. It really made national news. I'll just give you a little, this doesn't compete with videos of wildlife, but I'll just play this for just a minute so you can kind of see.
Tonight, the second part in our series on drinking water and the challenge of making sure that what comes out of our taps is safe to drink. Yesterday, we reported on a chemical that has been looked at by regulators for years and yet remains almost completely unregulated. Tonight, we travel to North Carolina, where residents near a chemical plant on the Cape Fear River have been dealing with the discovery of an unregulated chemical known as Gen X. While little is known about the health effects of Gen X, the discovery has alarmed local residents and reveals gaps in how we approach the regulation of drinking water. So this well tested at what?
This tested at 236.
In a rural pocket of Fayetteville, North Carolina, Mike Waters has 3 drinking water wells on his 5-acre property. But in the past 3 months, he's stopped using the water altogether. Well, when did you figure out your water wasn't safe?
6 September this year, we had no clue. We've been drinking the water, feeding it to our dogs, our parrots. We knew something was odd, but 6 September, Kenmore's came in. They had a letter said, we want to test your well. Do you give us permission?
A spin-off of the chemical giant DuPont, Chemours has a chemical plant just over a mile away.
Did you ever notice that?
Waters has lived here since 2012
All
with
right,
his wife and son.
let's
He's a veteran,
see.
former Special Forces, and
So that just kind of gives you a picture, and this contamination problem was really widespread. It affected the water supply for the city of Wilmington, which is the largest city on the coast of North Carolina. But my work has really focused on helping people like that, Mike Waters, with private wells. People with private wells, those are households that aren't connected to a public water system. So they're really in charge of making sure their water is safe. And if it's not safe, figuring out what they can do to make it safe. There's no support from professional engineers. And so those are the kinds of folks that I've been working with. So let me continue on. And so the state of North Carolina, I got involved really early on at the time, around the time Mike Waters discovered contamination in his well. The state had started testing private wells all around the chemical factory. So this is the Chemours facility. Again, it's southeastern North Carolina. At the time, the state didn't know much about the health risks from these chemicals, but they set a provisional health goal of 140 nanograms per liter, and the goal was to make sure nobody's water had more than that. And this map shows areas where they tested wells, and in the red, these are areas where wells turned up that had levels of Gen X above this 140 nanogram per liter standard. Yellow was detectable but less than 140 nanograms per liter, and green was not detectable with the methods available at the time. And I'll just say this was a very unusual pattern. The state had developed a model of where they expect to see contaminants, the traditional model kind of model that environmental engineers would use, and it would really predict contaminants are flowing this way. So you'd expect these high levels, but then you had red turning up here, over here. It's essentially, upstream, if you want to think of groundwater flowing this way. And so it really didn't make sense, and they couldn't figure out what was going on. But maybe this Gen X was coming from something else. Chemours was saying, well, maybe it's coming from people's septic tanks or sources that aren't us. It's not our fault. So I got involved. And the first thing we wanted to do early on, so this work has been I'm going to show you two pieces. The first part of identifying where was this coming from, was it sources other than the factory? That really took place in 2017 and 2018. And then I've come back more recently and said, well, how could we make a hybrid model that would be a combination of a Bayesian network with a more traditional model, and how would that work? And, how can we get the most accurate predictions? So that's more recent work. So, so for training this model, I was able to get from the state concentrations of Gen X that they had measured at about 1,200 wells. And then I had a wonderful postdoc who worked with me over many months to build a large curated data set. So at each of those well locations, he gathered information on that anything that we thought might be relevant to predicting the occurrence of Gen X. So that would include, for each well, what's the land cover around it? Because land cover can affect the transport of contaminants. What kind of soil? Soil characteristics also, the chemistry of the soil can influence the movement of contaminants in groundwater. What are the many other sources? Again, Chemours was saying this isn't our problem because this pattern doesn't match what we'd predict with our traditional groundwater models. So we got information about how far was each well from all of the other different kinds of potential sources of PFAS. It's used a lot in firefighting foam. That's why airports are up there. And then from well permits, we got information about the wells themselves, and then also we sent out surveys to the well owners. This ended up being a very wide data set, which is not ideal for machine learning. 422 columns, 1,205 rows. So just a quick note, originally we were focused on predicting whether Gen X would be above this 140 nanograms per liter target that the state had set. But just in 2024, the US EPA set a national drinking water standard of 10 nanograms per liter. Now, the Trump administration is undoing it. But so more recently, we've re-looked at our models and said, how well can we predict the risk of Gen X above this new standard? So data preparation, because we had this really wide, well, obviously discretization. Our initial discretization was just using R2 GenOpt in BayesiaLab. And then because we had such a wide data set, our first step was to reduce the dimensionality through data clustering, and then looking at which clusters were significantly correlated to the target and removing the clusters that weren't. And what's that? Oh, yes, 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 yes. Variable clustering, not data clustering. Variable, sorry about that. Clustering the variables. Then we unclustered the variables again, so we went back to the manifest variables, anything that was in a group of variables that showed to be significantly related to the target. And then we used augmented naive Bayes models with automatic variable selection, and I guess I don't need to go into all those details, but then the last step was kind of optimization by rediscretizing the variables and also looking at the structural coefficient. So we use BayesiaLab to train Bayesian network models. And then again, what I also wanted to do is say, okay, let's also do a direct comparison of Bayesian networks to our traditional kinds of models that I learned about as an environmental engineering student. And what these models do is they try to replicate the physical system. So here we have an area that's contaminated, the factory, the groundwater pollutants might leak from the factory underground, down through the soil, get into the groundwater. The groundwater is flowing this way, so they move along this way towards the river, like I said before. And what we want to do is predict what's at the well. Now, up in that corner, I added something to the diagram, which is air deposition. So at the time we got started, the state and groundwater modelers hadn't thought about including air emissions, and this factory had a big stack. It was emitting air. So I'm going to get to that later, but that's something you could include in a mechanistic model. You could say, let's also model what's coming out of the stack, depositing on the land all around the factory and getting down into the ground. So the way these mechanistic models work, they're numerical models. You basically divide the underground into what looks like a stack of Lego bricks. So every brick is a little unit, and what you do is you look at, so if that's one Lego brick right there, you look at what contaminants are flowing into the Lego brick. Are they reacting in any way when they're there, like chemically transforming or biodegrading? And then what flows out, and then it goes into the next brick, and that's the inflow to the next brick. So they're numerical models, and they're computationally very expensive. Another problem is you can't make predictions at locations where you have missing data. One of the key variables that you need to have is you need to know the depth of the well for which you're trying to predict risks. And in our case, we didn't have any well depth information. We sent surveys to all 1,205 people whose wells we had information about. And we also looked for well records. And with that, we were only able to get well depths for about a third of the wells. So that's a lot of missing information, meaning that our traditional model couldn't make any predictions for anything that we didn't have an exact depth for. They're also really time consuming to build and run. Like for this model that we built, it was 150 hours of computing time just for one run after the model was already built. So we built two types of hybrid models, and here's an area where I could use advice because I kind of made this up. So I'm guessing Lionel knows better ways to do this. But one was what we're calling a simple model. So the groundwater model, where the traditional model has two parts. One is figuring out where is the water flowing, how much water is moving from one Lego brick to the next. The other part is, once you know that, how are the chemicals moving with the water? And then, there's extra stuff that happens. They might react, they might stick to the soil and so forth. The groundwater flow part runs in less time. Takes about 75 hours to run for one run. So we made a simple Bayesian network model where we just took the flow predictions that told us at any location, which way is the water flowing, how fast is it flowing. And then we made a more complex one where we took the prediction from this traditional model of what's the actual concentration of Gen X that we expect to see at that well, and use that as input to a Bayesian network model. So those are our models. What ends up with is we built many models, 14 models to be exact. So we had the mechanistic model, a Bayesian network model just trained on our original observational data, the simpler model with just groundwater flow information as input, and then the more complex model. And we wanted to look at 2 different thresholds for Gen X, the original one, 140 nanograms per liter, and then the new EPA standard. But, oops, this is right. So the mechanistic model can't make predictions for wells without well depth. So we could really only run this model for the 424 wells for which we had depth information. So we could run that one. But I pointed out to my team a whole benefit of the Bayesian network is we can make predictions without complete data. So we ran these other Bayesian network alone and hybrid models with the full data set, and that should say 1205, not 1204. And then we did 5-fold cross-validation, multiple runs of that, and we looked at several different performance metrics. As folks in this room know, the area under the receiver operating characteristic curve just gives a general indication of how well a model separates contaminated wells from not contaminated wells. But in my field, we're much more worried about false negatives. We don't want to tell people their water's safe to drink, and it turns out we were wrong. And so we also want to look at how well the model identifies kind of these true positives without too many false alarms. So we had a couple metrics for this, the area under the precision recall curve, and then again, because in the environmental field, we really care about avoiding false negatives. There's the area under the F2 curve, which assigns a lot more value to avoiding false negatives, so missing wells that are really contaminated. So we look at these metrics. The first one is really the early result. The state wanted to know, where is this contamination coming from? And again, I did this many years ago in BayesiaLab, and it was really quite amazing. No matter, we tried many different iterations and everything, but in every model, it turned out that air deposition turned out to be important. Now, why did I get information about air deposition? That we included as one of our 422 variables in the wide data set, because I went back and I read about West Virginia from 15 years earlier, and the articles I read said, well, actually, they had discovered that there were atmospheric emissions from the plant. So I thought, well, we better look at that too. And so we had information about how much mass of this Gen X had been released through the factory stack over the years, and came up with, when the factory was operating at steady state, how much Gen X was it depositing all around per unit area. And so that was, these variables here, what we're trying to predict is Gen X above 140 micrograms or nanograms per liter, and then the variables are arranged in order of their mutual information with the target node. I might have got that wrong. I'm a little bit rusty, but I can't remember if it was correlation or mutual information. But that air deposition turned out to be really important. And interestingly, none of the other things that were suggested as potential alternative sources, like maybe firefighting foam from airports or people's leaky septic systems, turned out to be retained in this final model or any of our kind of intermediate models. And that led actually the North Carolina Department of Environmental Quality to tell Chemours that they had to put emissions controls on their stack. So that was an immediate outcome from that work. So anyway, that was really beneficial, like I said. so our next step more recently, I said, well, what if we build a better mechanistic model and we add air deposition to the original groundwater model? Will it then compete with the Bayesian network? Will it give us a more accurate idea of what's going on? So I'm going to get to the performance comparisons of the different models in a minute, but what happened here is, so this is showing that even when we add those predictions from our updated improved groundwater model, air deposition remains important. So the mechanistic model wasn't accounting for all of it. But there's the mechanistic model contaminant concentration prediction. It is the most important now in predicting whether Gen X is above 140 nanograms per liter. But again, these other variables that we originally found stayed in the model. That's some of the groundwater flow predictions. So, anyway, yeah, so I'm interested, there might be better ways to do this, to integrate these two really different modeling approaches, but not knowing what I was doing, I thought, well, this is a way to start. So now the second question is, which model is more accurate? Our groundwater modelers, when I got started on this kind of work, were really skeptical of Bayesian networks, and it was really hard to even get this kind of work published in an environmental engineering journal, because it's not what their people are expecting. They're expecting the traditional numerical model. So what's more accurate? The mechanistic model, the original approach, a Bayesian network just trained on data, or one of my hybrid models? And again, we had these many different models we were comparing, some trained on the full data set with missing data, some only on the observations with complete data, for two different thresholds of concern, 140 and 10 nanograms per liter. So this is a lot going on. I apologize, I didn't have time to make better charts. We're in the process of finishing a manuscript, and this is directly from a manuscript, but I'll walk through it. What I'm showing here is, these are the different metrics of performance. So the area under the rock curve, that's this cluster of bars. This is just the general ability to trade off false positives and negatives. This is the cost of, the area under the precision recall curve, which again is better for looking at making sure you don't miss any of the contaminated wells or miss fewer of them, and then area under the F2 curve. And let me see, I've got some animations to try to help explain this. This first cluster of bars in the lighter colors, this is for the models that predict whether Gen X is above this new standard that EPA is trying to set of 10. It's a lower standard. And let's see, then the darker cluster of bars, let's see, show you what this is. This second set of bars in each case is for the original 140 nanograms per liter standard. But the important thing to notice, so on the left is always, this is the mechanistic, the traditional groundwater model, traditional groundwater model, traditional model, traditional model, traditional model, traditional model. And higher is better, and the traditional model never does better than any of the Bayesian network models. So this Bayesian network, the initial one, we built a curated data set. That took time, but then it ran pretty quickly, made much better predictions. And then if you actually add the mechanistic output to the Bayesian network, that's these ones here, the more complicated hybrid model, that really is, you do get better performance by combining these two approaches. So maybe that's a wrong thing to do. I don't know. Let's see. Now, these results that I showed you, this was just for the complete data. So this is the 424 wells. We have all of their depths and other information. And then I thought, well, let's also look at how well these predict when we have missing data. So the comparison here is, let's see, did I get that right? Yes, so the ones in the green box here, this is when we take the full data set, meaning that about 2/3 of the observations have important missing piece of information. The depth of the well is missing. This is our original models where we know the depth of the well. And because, you need the depth of the well to make a prediction with the traditional kind of mechanistic model. We can't do that for this full data set. So you see these predictions on these same three metrics, they're not quite as accurate when 2/3 of our well depths are missing, but still good. And yeah, and you know, still do well even with a lot of missing data compared to the mechanistic model. So kind of the key finding, the first thing was that just a Bayesian network initially really helped the Department of Environmental Quality uncover where this pollution was coming from and control it. A second finding is that the Bayesian networks actually provided more accurate predictions than the traditional modeling approach at a much lower computational cost. Remember, 150 hours for one run of a traditional mechanistic model. And then if you incorporate the Bayesian network or the mechanistic output into a Bayesian network model, we did get some improved performance. So with that, we've got some publications on this. The first one listed is the original work where we figured out that it was really air deposition that was driving the pattern of contamination that was seen. The second two are looking at Bayesian networks to predict the occurrence of PFOA, which is the original kind of PFAS of concern, around a site in Minnesota. So those are a different topic that I didn't talk about, and that what I presented today, we're in the process of getting ready to send for publication. But my questions for this expert audience, what other approaches are out there if people tried for taking a traditional model that's based on kind of first principles of physics, chemistry, biology, and a picture of what we think is going on into a Bayesian network model? And then less important for now, but my dimension reduction approach, I'm not sure quite if that was correct, again, to cluster the variables, eliminate ones that were associated with clusters that didn't have a significant correlation with what I'm trying to predict, and then unclustering and learning from those. So those are my questions for the audience.